All right, so the last thing we need to talk about with limits is what happens when we throw infinity into the mix. And so a good place to start is to talk about the end behavior of a function. And this is a good start because this is something that you discuss a little bit in pre-calculus or in algebra classes. What happens sort of as the function goes off to infinity. And that's what we mean here. So we're going to give a very precise way to talk about the end behavior of a function. So what we mean by the end behavior of the function is the limit as x approaches infinity of the function. So basically, if I just trace the graph all the way off to the right as far as I can go, and then the limit as x goes to minus infinity. So that's tracing the graph of the function all the way to the left. So together these give us the end behavior of a function f of x. Okay, so now in the case that one of these two limits actually equals a number, so now it could be the case that they don't equal a number, so they could equal infinity or minus infinity, and we'll see some examples of that. But in the case that one of them equals a number, so the limit as x goes to infinity of f of x equals some number L, or limit as x approaches minus infinity equals L, then f is said to have a horizontal asymptote. At y equals L. And so notice that the horizontal asymptote is really a horizontal line. Okay? And I hope this is a concept that's familiar to you. But notice now that we're defining it in terms of having an infinite limit. So having a limit as x either goes to infinity or minus infinity. So you can think about the function is leveling off in one or both directions to the line y equals L. And we'll see a picture of this in just a minute. Okay, so let's actually look at a couple of examples. So first of all, notice that if we take the limit as x goes to infinity, or minus infinity, it doesn't matter. So we'll put plus or minus infinity, because it won't make a difference, of the function 1 over x. So let's just think about what this is saying for a minute, just from a purely arithmetic standpoint. We're taking x and we're letting x get really, really big. And now I'm going to start a convention that when I say big, I mean far away from 0. So I don't mean big as in a positive big number, like a negative number is smaller than a positive number. I don't mean that. I mean really the distance from 0. So a big number, when I say big, is going to be far away from 0. And then a small number is going to be close to 0. So going back to this example, what I'm saying here is that whether x is going to plus or minus infinity, x is getting very big. It's getting far away from 0. So I'm taking that number, I can think about it as just a very, very big number, and I'm reciprocating it. I have 1 over a very big number. So just think about 1 over 100, 1 over 1,000, 1 over a million, 1 over a billion. Those numbers are getting very small, closer and closer to 0. So this limit is actually approaching 0. And we'll kind of start this convention that when we have something like 1 over a big number, so in a limit here, I'm just thinking about x is becoming a big number, that's getting close to 0. And we can actually generalize this a little bit. So if n is bigger than 0, and now here n can be any real number, then this is still going to be true if we replace x with some power of x to the n. So 1 over x to the n is also going to be 0, because if I take a big number and raise it to a positive power, I'm still going to have a big number. And I'm still taking 1 over a big number. So that's giving me 0. So another way we can see this is that the line y equals 0, so in other words, the x-axis, is a horizontal asymptote. Of this function. Okay, so here's kind of a preliminary example. And it's actually going to be a very important example. When we talk about rational functions, we're going to use this fact over and over again to simplify limits. So an interesting question comes up. We see that this function has 1 horizontal asymptote. Now, of course, a function could have no horizontal asymptotes. For instance, the function y equals x does not have a horizontal asymptote because it does not level off to a horizontal line. It actually goes off to infinity to the right and then negative infinity to the left. So how many horizontal asymptotes can a function have? It can have 0, 1, and it can have as many as 2. And this is more or less just a property of the vertical line test. So the function can't be leveling off to 2 different lines. So 2 horizontal asymptotes. And we'll actually see an example of a function that does have 2 horizontal asymptotes. And I'll just tell you what it is right now. So for instance, the function x over absolute value of x plus 1. And we'll actually show that this function does indeed have 2 horizontal asymptotes. So let's start out by talking about the end behavior of polynomial functions. So what we want to do is let p of x be a polynomial of degree n and leading coefficient so remember that's the coefficient in front of the leading term, or the power of x that's the highest. So the leading coefficient is a. Okay, so this table here summarizes the end behavior of the polynomial. Now the end behavior of the polynomial depends on whether or not the degree is odd or even, and then whether or not the leading coefficient is positive or negative. So let's just draw a few sketches of what this could look like. So we'll say this is case 1, this is case 2, this is case 3, and then this is case 4. Okay, so let's look at case 1. So let's draw our coordinate axes just real loosely. Again, this is just going to be an example. So we know that the leading coefficient is positive and the degree is odd. So if you want an example, just think about x cubed. Now we don't know what happens in the middle because this is just a general polynomial, but all we care about is the end behavior. So as x goes to minus infinity, our polynomial is going to minus infinity, and then it's going to move around, do whatever, but eventually it's going to shoot off to infinity. Because as x goes to infinity, the polynomial is also going to infinity. So then for 2, let's draw a similar graph to show the end behavior. So now the degree is even and the leading coefficient is still positive. So we're actually shooting off to infinity in both directions. Now I don't know what happens in the middle. Maybe it wiggles a little bit, I don't know. But all I know is the end behavior as x goes to minus infinity. So of course this is the x-axis. As x goes to minus infinity, the polynomial is going to infinity, just like when x goes to infinity, the polynomial is going to infinity. Okay, so let's look at the third case. So the third case is similar to the first case, except the leading coefficient is negative instead of positive. So this is just going to switch both of the end behaviors. So now, as x goes to minus infinity, we'll be going off to infinity, and then we may wiggle around some, I don't know, but as x goes to infinity, the polynomial will be going to minus infinity. And then finally, the fourth case is going to be exactly like the second case, except because the leading coefficient is negative, in this case, as we see here, the degree is even, our function is going to be going off to minus infinity in both directions. And then it's going to wiggle, do some whatever, and then go off that way. So this is the case for polynomials. One of these 4 cases will be what's going on. Now I should say that here n is really a positive number. Okay, so if n were equal to 0, if it was a degree 0 polynomial, actually it would just be a constant function. So actually the function itself would be a horizontal line, and so of course it would have a horizontal asymptote. It would be its own horizontal asymptote. So this is really the cases that occur when the degree of the polynomial is positive. Okay, so this is a graph of 2 functions, g of x in blue and h of x in red, that have some horizontal asymptotes. So notice that these green dashed lines are the horizontal asymptotes. So there's one at y equals 0, y equals 1, and y equals negative 1. So y equals 0 is a horizontal asymptote for the function g of x. And that's because if you look, as x goes to minus infinity, so it gets further and further away from 0 to the left, this function is leveling off to the line y equals 0. And the same thing happens as x goes to infinity. So as x gets bigger and bigger, further away from 0, to the right, we're also leveling out to 0. Now, the case for h of x is a little bit more interesting because we see that y equals -1 and y equals 1 are horizontal asymptotes. And why is that? If I look as x goes to infinity, so as x gets big to the right, then the function is leveling off to y equals 1. But then in the opposite direction, as x gets big going to the left, further away from 0, we're leveling off to y equals -1. So both of these lines, y equals -1 and y equals 1, are horizontal asymptotes for this function h of x. And I get asked this question a lot when I teach this, whether or not a function is allowed to cross a horizontal asymptote. So for instance, if this function here, so it's leveling off to this dotted green line, would it ever be okay for it to maybe come up and then level off or something like that? That's perfectly fine. Functions can cross horizontal asymptotes. And actually you see here, these functions do cross some horizontal asymptotes there. But it's a good question. When we talk about vertical asymptotes, that will not be the case. Functions will not be able to cross vertical asymptotes. Okay, so now we're going to review rational functions. And again, in a course of pre-calculus, you probably talked about these rules about rational functions and their end behavior. But actually, we're going to be able to use the limit laws to derive these rules in special cases. Okay, so first of all, just let me note that p of x is a polynomial of degree n and leading coefficient a. And then q of x is also a polynomial of degree m and leading coefficient b. Okay, so this table here summarizes the end behavior of these rational functions, or in other words, it gives the horizontal asymptotes of these rational functions. And recall that a rational function is just a quotient of two polynomials. And here we're just saying the polynomial in the numerator is p of x, and the polynomial in the denominator is q of x. So if we look at n versus m, so the degree of the numerator versus the degree of the denominator, if the degree of the numerator is greater, there's no horizontal asymptote. Or in other words, the end behavior of the function is going off to plus or minus infinity. If the degrees are equal, so the degree of the numerator equals the degree of the denominator, we have a horizontal asymptote at y equals a over b. And then finally, if the degree of the denominator is greater, then we have a horizontal asymptote at y equals 0. Okay, so now these rules are just told to us in pre-calculus, but actually in calculus we're going to be able to prove them. And now we're not going to prove them in general, but in special cases, we're not just going to blindly apply these laws. We're actually going to use calculus to see why this is. So given a rational function, we can actually just manipulate it and use the limit laws to figure out exactly what the limits at infinity will be, or in other words, what the horizontal asymptotes will be. And we'll see how to do that in a few examples, but this is just a reminder that we do have this rule from precalculus that tells us how to find the end behavior of a rational function. So I want to talk about one more special case with rational functions. So let's say that we have a rational function given by the quotient of two polynomials. Again, we'll just call them p of x and q of x, where p of x has degree m. And then, now I'm going to consider this special case where the degree of q of x is going to be 1 less than the degree of p of x. So the degree of the denominator is m minus 1. So the degree of the top is 1 greater than the degree of the denominator. So in this case, f of x has what's called a slant or oblique, sometimes, asymptote. And so if you believe the rules on the previous page, this function, because the degree of the numerator is greater, doesn't have a horizontal asymptote. It's actually going off to infinity or minus infinity as x goes to plus or minus infinity. But it does have what's called a slant asymptote. So it's actually leveling off to infinity, but it's leveling off along the equation of a line. Okay, and I'll show you a picture on the next slide. So this is an example of a function exactly like we were talking about on the previous slide. X squared plus 1 over x plus 1. It's a rational function. It's the quotient of two polynomials. The degree of the numerator is 2. The degree of the denominator is 1. So the degree of the numerator is 1 more than the degree of the denominator. So we know that it has a slant asymptote given by, well, we have to do a little bit of work, and we'll see in an example actually how you find the slant asymptote. But we see that the slant asymptote is given by y equals x minus 1. So this is the slant asymptote. So we say that f of x has y equals x minus 1 as a slant or oblique asymptote. And what happens with the function is really interesting. So see that as x goes to either plus or minus infinity, the function isn't leveling off to a horizontal line, it's actually leveling off to this slanted line, hence the name slant asymptote, not horizontal asymptote. So it's actually really simple in concept. Now I will say that to actually find the slant asymptote given a rational function, you need to be able to do polynomial division. So the way you find the slant asymptote is you actually just divide the denominator into the numerator, and then the quotient term is actually going to be the slant asymptote, as we'll see. Okay, so this is just an example, but hopefully it illustrates the idea of what a slant asymptote is. So it's just another way that even if we don't know a function has a horizontal asymptote, it may have a slant asymptote. So it's just another way to describe the end behavior of a function. So the final type of asymptote we need to talk about is the vertical asymptote. And this one can be a little bit tricky. So again, we're going to start with the function f of x. And the idea is if we have a fixed number a, so if the limit is x approaches a from the right of f of x is equal to plus or minus infinity, or the limit is x approaches a from the left of f of x is plus or minus infinity, so it grows without bound as x approaches a from the left or from the right, then x equals a is a vertical asymptote of f of x. Okay, so we can look at a couple of really important examples, and these will actually probably be the most important examples that we look at. So the limit is x approaches 0 from the right of 1 over x is equal to, well, let's just think about it. Okay, so remember kind of our convention is that when we say a big number, we mean a number far away from 0. And when we mean a small number, I mean a number close to 0. And so a small positive number is a number just to the right of 0, like in this case. And then a small negative number is a number just to the left of 0. So here, just think about what's happening when I divide 1 by numbers that are getting closer to 0 but remaining positive. So 0.1, 0.01, 0.00001. As I take 1 and I divide it by smaller and smaller numbers, my number is getting larger and larger. And because these small numbers are remaining positive, I'm getting a large bit, or a big, in the sense that we were saying before, positive number. So as x approaches 0 from the right, 1 over x is going to positive infinity. Also, if you just know what the graph of 1 over x looks like, this is not too hard. And similarly, by similar reasoning, except now, if I go from 0 from the left, my small numbers are remaining negative. So when I flip them, I'm getting a big number, but that big number is remaining negative. And like I said, we can actually deduce all of this information from the plot of 1 over x. So if we plot y equals 1 over x, that just looks like this. It actually has a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. So you see, as x approaches 0 from the right, we're going to infinity, and if we approach 0 from the left, we're going to minus infinity. So it's a very simple application, but as I said, it will come back again and again, and we will typically be able to reduce problems of finding vertical asymptotes to one of these two cases, whether we're going to plus infinity or minus infinity, to then justify why we have a vertical asymptote. So here I have plotted a couple of functions with vertical asymptotes. So let's just go ahead and say what they are. So the blue function, 1 over x, we've actually already said that this function has a vertical asymptote of x equals 0. So in other words, x equals 0 is a vertical asymptote of g of x. And we see that x equals -1 is a vertical asymptote of h of x. Okay, so let's explore kind of the possibilities that are being highlighted here. So for g of x, we see that actually as x approaches 0 from the left, we're going to -infinity. And as x approaches 0 from the right, we're going to infinity. So actually, the function is going to, or is getting big in two different directions. But for h of x, as we approach -1 from the left and -1 from the right, we're both dive bombing to -infinity. So you see, it really doesn't matter whether we're going to plus or minus infinity from one direction, or both directions, whatever, as long as we have one of those two conditions, we're really getting a vertical asymptote. And notice that a function cannot just pass right through a vertical asymptote. That's going to be a problem. Okay, because somehow the function is supposed to be going to plus or minus infinity, so it's not going to be able to just go right through it. So up until now, we've really only discussed polynomial functions and rational functions and kind of variations thereof. So I thought I would just conclude this topic by giving you just a few other functions, an exponential function, the logarithm function, and some of the trig functions, and just sort of illustrate to you what the end behavior looks like and whether or not there's any vertical asymptotes. Okay, so first of all, let's look at e to the x. So the limit as x goes to infinity of e to the x, well, this represents exponential growth. This is going to infinity. And the limit as x goes to minus infinity is going to 0. And this is clear from the graph of e to the x. It's going off like that. It's leveling off to 0. So in other words, it has a horizontal asymptote at y equals 0, or of y equals 0. And it's growing exponentially. So it's going to infinity as x goes to infinity. Now the inverse of the exponential function is the logarithm function. And so here we'll think about the natural logarithm. So the limit as x goes to infinity of natural log of x is also infinity. And we can actually see that from the inverse relationship of the exponential function and e to the x. Sorry, the exponential e to the x and the natural logarithm. Now, we got to be a little careful in the other direction because the domain of natural log of x is just x strictly greater than 0. So if we look at the end behavior, we better approach 0 from the right. Okay? And in that case, we're going to get, again, just think about the inverse relationship between these two functions, we're going to get negative infinity. And again, we can look at the plot of this graph and see why that's the case. So this is what log x looks like. And you see, as x goes to, as x approaches 0 from the right, the function is dive bombing to negative infinity. So there is a vertical asymptote at x equals 0. And then as x goes to infinity, we're just shooting off to infinity. Now the trig functions have a problem. So let's think about the limit as x goes to infinity of sine of x. Now the problem is sine as x goes to infinity is just oscillating between 1 and -1. it's never leveling off to just one number. So this limit really does not exist. And that's going to be the same whether this is plus or minus infinity. And it's also going to be the same for cosine, because cosine also oscillates indefinitely between 1 and minus 1. But what we can do is look at the tangent function. So remember that tangent is sine over cosine, and it's periodic. And so if we just look at one period between negative pi over 2 and pi over 2, we can look at so we'll have to approach negative pi over 2 from the from the right of tangent. And then we'll have to approach pi over 2 from the left. And so maybe to make this clear, let me draw one of the periods. So here's pi over 2. And here's negative pi over 2. And so the graph of tangent looks like this. And the reason it looks like this, so there really are vertical asymptotes here and here. So this is going to be negative infinity, and this is going to be infinity. And the reason this is the case is because tangent is really sine over cosine. So as x approaches negative pi over 2 from the right, cosine is going to what? Okay, so cosine is going to be going to 0, but it's going to be remaining positive. And then sine is going to be going to 0, but it's going to be negative. Sorry, it's going to be approaching negative 1. The limit is sine as x approaches negative pi over 2. Sine x is negative 1. So this is really like negative 1 over a small positive number, which is going to minus infinity. And then here, as x approaches pi over 2 from the left, cosine of x is still going to 0 while remaining positive, but sine x is now positive. So this is a positive over a small positive number, which is going to be infinity. Okay, so that's just to kind of give you a picture of what these other functions do, where their vertical asymptotes are, what their end behavior is. So these are useful limits to remember, and they'll show up from time to time. Okay, so we want to jump in and find the end behavior of this function. So we're going to take the limit as x goes to infinity, and as x goes to minus infinity. So in the sense of the way we're taking this word, we are only interested in x values that are big. Now, big positive numbers and big negative numbers, numbers that are just far away from 0. So we can actually conclude that x is not 0, because we want to think about x being far away from 0. Now, the way you solve these problems, okay, you're going to do it the same way every time. Here's what you do. Factor out the highest power of x from the numerator and the denominator. Okay, so what I mean is the highest power of x from the numerator is x cubed. So I'm going to rewrite this function as x cubed times 1 minus If I factor out an x cubed from 3x, I'm going to get 3 over x squared, and then plus 1 over x cubed. Okay, so you see if I just distribute back in x cubed, I'm going to get the numerator I started with. Now the highest power of x from the denominator is x squared. So what am I going to be left with? Well, I factored out an x squared, so I'm left with 1, and then minus 1 over x squared. And same thing, you can verify that when I distribute the x squared back in, I get the same thing. And now, because I can assume that x is not equal to 0, what I can do is I can actually cancel, well, 2 of the factors of x. So I can divide by x, because I'm assuming that x is not equal to 0, because I only care what happens far away from 0. So if I want to take the limit, so in other words, let me simplify this down. This is just going to be x times 1 minus 3 over x squared plus 1 over x cubed over 1 minus 1 over x squared. And I can just take the limit. Let's just say as x goes to infinity of x times 1 minus 3 over x squared plus 1 over x cubed over 1 minus 1 over x squared. But now let me apply the limit laws. So if I look at this term and let x go to infinity, this is going to go to 0. This was that fact that we stated, that the reciprocal of a positive power of x is x goes to infinity is always going to go to 0. So look at how many terms are going to go to 0 here. That's going to go to 0. This is going to go to 0 in the limit. And so all I'm left with is 1 over 1 times x. So this is really equal to, just applying the limit laws, the limit is x goes to infinity. And of course, all of this is equal to the limit as x goes to infinity of f of x. Okay, so all I'm left with is just x. But I know the end behavior of polynomials. As x goes to infinity, well, x is going to infinity. And I can do the same thing if I take the limit as x goes to minus infinity. By just rewriting the function and assuming x is not equal to 0, that's negative infinity. This is just the limit as x goes to minus infinity of the same thing. But the same thing is going to happen to all of these reciprocal powers of x. They're all going to go to 0. Zero, 0, 0, because I'm dividing by a big number. It's going to 0. So this is just the limit as x goes to minus infinity of x, which is going to minus infinity. So here's the end behavior of my function. As x goes to infinity, I'm going to infinity. As x goes to minus infinity, I'm going to minus infinity. And notice that that means that there are no horizontal asymptotes. Because the only way I'm going to have a horizontal asymptote is if one or both of these limits are equal to a real number. So here we're going to follow the same strategy. We're going to rewrite this function assuming that x is not equal to 0 in a special way. So I'm going to factor out the highest power of x. So I'm going to be left with x cubed, that's the highest power of x, 2 over x squared minus 1. And in the denominator, I'm going to have x cubed times 2 plus 1 over x squared. Which, again, assuming that x is not equal to 0, I can cancel the x cubes. And I'm just left with 2 over x squared minus 1 over 2 plus 1 over x squared. Okay, perfectly valid. So then the limit as x goes to infinity of f of x is equal to the limit as x goes to infinity of this guy. Because again, I can assume that x is not 0. X is going to be very big. But look at what happens to these reciprocal powers of x. Here and here. They both go to 0. So what that means is I'm left with negative 1 over 2. How cool is that? So that means that we know the end behavior, at least as x goes to infinity. Let's go ahead and take the limit as x goes to minus infinity. And it may not surprise you that really nothing is going to be different. Everything's still valid. We can assume that we're far away from 0. But now we have a large negative number. But these reciprocal powers of x are still going to 0 by just applying the limit laws. It doesn't matter whether I'm dividing by a large positive number or a large negative number. A fixed number over a big number goes to 0. So this again is just equal to negative 1/2. So here's our end behavior. But what does this tell us? It tells us that we have a horizontal asymptote. So specifically, y equals negative 1/2 is a horizontal asymptote. So this is a function that we've seen already, and it was an example of a function that we said had 2 horizontal asymptotes. So let's see why. Well, notice that because of the absolute value, we have to treat this like a piecewise function. So when x is bigger than negative 1, well, what does that mean? That means that what's inside the absolute value is going to be positive. So we can just remove the absolute values. So f of x really is just x over x plus 1. But if x is less than negative 1, what's inside the absolute value is actually going to be negative. So we actually need to multiply the denominator by negative 1 to remove the absolute values. And notice that x plus 1, that quantity times negative 1, is negative x minus 1. But now we can take the limits as x goes to plus or minus infinity. So the key is that when we're taking the limit as x goes to infinity, we want to use this first definition. Because as x is a big positive number, x is certainly going to be bigger than negative 1. So this is just the limit is x goes to infinity of this guy. And if I do my now familiar trick, factor out the highest power of x, I'm taking the limit of x over x times 1 over 1 plus 1 over x. Okay, but since I'm far away from 0, I can just cancel this. This is going to go to 0. And so what I have is just the limit of 1, which is 1. Now, you can see what's going to happen is x goes to minus infinity. Everything is going to be the same, except I'm going to have to use this bottom definition. Because as x goes to minus infinity, x is certainly eventually going to be less than negative 1. So the limit is x goes to minus infinity of x over negative x minus 1, which is the limit, is x goes to minus infinity of x over x times 1 over minus 1 minus 1 over x. And again, I'm just factoring out the highest powers of x. I can assume that x is far away from 0, so I can cancel. And so also, this guy here is going to 0. The limit of 1 over x as x goes to minus infinity is 0. So I just have the limit is x goes to minus infinity of negative 1. 1 over negative 1 is negative 1. So this is negative 1. So here's my end behavior of my function. And notice that this tells us we have two horizontal asymptotes. Y equals 1 and y equals negative 1 are horizontal asymptotes. Okay, so we already mentioned this function a little bit, why it has a slant asymptote. The degree of the numerator is 1 higher than the degree of the denominator. And we can almost think about this function as an improper fraction, in the sense of just a rational number, like 5/3. We can actually just write it into its proper form. So 5/3 is 1 and 2/3. That's sort of like what we're doing here. So what we want to do to find the slant asymptote is to actually divide x plus 1 into x squared plus 1. So let's just do it. And notice here that I'm writing x squared plus 1 is x squared plus 0x plus 1, just like if I divided 10 into 101, I would put 101. Okay, so x goes into x squared x times, so we'll just bring that down, x squared plus x, and then subtract. So that's 0, and then we have minus x, and then plus 1. Okay, and then x plus 1 goes into minus x plus 1 minus 1 time, and then we get minus x minus 1. Subtract, we'll get negative 2. X does not go into negative 2, so then we have a remainder of negative 2. All that to say, we can rewrite this function is x minus 1. Oh, getting ahead of myself. This is 1 minus a negative 1, so 2. So the remainder is 2. There we go. It's not going to affect the slant asymptote, but we should try to do it correctly if we can. Okay, so this is the quotient when we divide these two, and then plus the remainder, and then what do we do with the remainder? We divide it by, well, whatever we were dividing, in this case, x plus 1. So x plus 1 was the divisor. So that goes underneath the remainder. But writing the function in this way actually makes it very obvious what the slant asymptote is. So notice that the limit as x goes to infinity of 2 over x plus 1 is 0. And now without doing all the tedious work, you can just see that, okay, 2 is fixed, x plus 1 is getting really, really big. So it's just a number over a really big number that should be going to 0. So the point is that this term is going to 0 as x goes to infinity. So more or less, the function is starting to look more and more like x minus 1 far away from 0 when x is big. So what that means is that y equals x minus 1 is the slant asymptote. So that's how it goes. Okay, so here we have some more limits of functions that we want to find the end behavior of. Now notice that these are sine functions, so you may be putting up a red flag and saying, well, wait a second, I thought the limit as x approaches infinity of sine does not exist. And now that's true, but this is not the limit of sine of x. It's the limit of sine of 1 over x. So I really need to think about what's going on with 1 over x. And here I'm also going to use the continuity of the sine function. Okay, so I'm going to really be able to take the limit and then just evaluate sine of whatever that limit is. So the key observation here is that as x goes to infinity, 1 over x approaches 0. But it doesn't just approach 0, it actually approaches 0 while remaining positive. So I'm going to put a plus here. So it approaches 0 from the right. So now if I let t equal 1 over x, what is that going to tell me? Well, what that tells me is that I can actually replace, okay, as x goes to infinity, what's happening to t? T is approaching 0 from the right. So what I can do is I can write this as the limit as t approaches 0 from the right, because as x goes to infinity, t, which is 1 over x, is approaching 0 from the right. And then the argument is 1 over x, except I've let t equal 1 over x. So this is really just the limit of sine t. But this is a limit we talked about in the last lecture. This is just equal to 0. And again, I'm using the continuity here because really I'm just saying that t is going to 0, so then I can just evaluate sine of 0, which is 0. And I can do exactly the same trick here. So I can say, again, let t be 1 over x, so that as x goes to infinity, t is approaching 0 from the right. Now, x is going to be 1 over t, and then again we have sine of t, right? But this is just sine t over t as t approaches 0. So this should just be going to 1. So our first limit is 0, and our second limit is 1, based on the known limits that sine t goes to 0 as t goes to 0, and sine t over t, which is this, goes to 1 as t goes to 0. Okay, so here we have a rational function, and we're looking for the limit. In this case, a is equal to 1, so the limit as x approaches 1 from the right and from the left. That's what I mean by this plus or minus right here. And then we also want to see if there's any vertical asymptotes for these functions. Okay, so the first thing we're going to do is we're going to notice that in this function, because we're taking the limit as x approaches 1 from the right and left, we can actually assume that x is not equal to 1. And in that case, we can actually write f of x in a different form. So I can factor the numerator and the denominator. So the numerator is a difference of cubes, so it factors as such. And the denominator is actually x minus 1 squared. So what we can do is we can actually cancel one of the factors of x minus 1 because we're assuming x is not equal to 1. And again, this is only true because we're assuming x is not equal to 1. So then when we take the limit, so let's just do from the right first. So the limit as x approaches 1 from the right of, well, of course, of f of x is going to be the same thing as the limit as x approaches 1 from the right of x squared plus x plus 1 over x minus 1. Now the first thing I'm going to do here is I'm going to use the limit laws. And the limit laws tell me that I can plug in 1 where I'm able to. And if I get a limit, that is what the limit is. So the numerator is a polynomial, and if I just evaluate it 1, I see that that's actually equal to 3. So the numerator is approaching 3. So I'm getting a factor of 3 here. And then the rest of the limit, so what I have to take the limit next, is this 1 over x minus 1. Okay, but this is actually not too bad because I just have to think about x is going to be a little bit bigger than 1 because I'm approaching 1 from the right. And if x is a little bit bigger than 1, then this denominator, a number a little bit bigger than 1 minus 1, is going to be a small number that's positive. So this is going to be 1 over a small positive number. So that's approaching positive infinity. So this is really 3 times, and then this limit here is infinity. It's an equals. So then the whole thing, if I take 3 and multiply by infinity, I'm just going to get infinity, of course. And I mean, the real way to think about it is, okay, I'm multiplying this by 3, but it's just getting larger and larger and larger and staying positive. So it's just going to infinity in the limit. Okay, so then the limit as x approaches 1 from the left, I can do exactly the same thing. So this is going to be, because I can assume x is not equal to 1, the limit is x approaches 1 from the left of, again, x squared plus x plus 1 over x minus 1. The numerator is tending to 3, so I get a factor of 3. And then I just multiply by the limit as x approaches 1 from the left of 1 over x minus 1. But now here, it's very similar to this case, except now x is approaching 1 from the left. So x is less than 1. And if I take a number less than 1 and subtract 1, I get a negative number. So this is going to be 1 over a small negative number. But that's going to be tending towards negative infinity. So this is just going to be 3 times something that's tending towards negative infinity. The 3 is not going to make a difference. I'm just going to get negative infinity. So we see these are the limits as x approaches 1 from the right and 1 from the left. And this is more than sufficient to tell us that we have a vertical asymptote, specifically at x equals 1. Okay, so another rational function, and we're trying to take the two-sided limits as x approaches 1 and then as x approaches negative 2, and then see if there's any vertical asymptotes. So let's look first at the case a is equal to 1. So before I even start taking limits, let me actually just simplify what f of x is. So notice that f of x, I can factor the numerator and factor the denominator. So the numerator is x plus 2 squared. So you can see if you just FOIL that back out, I'll get x squared plus 4x plus 4. The denominator factors is x plus 2 times x minus 1. Okay, so now for a equals 1, let's take the limit as x approaches 1, we'll start from the right, of x plus 2 squared over x plus 2 times x minus 1. Okay, but now we can start by using the limit laws. So these factors of x plus 2 are all approaching 3. So in the numerator, as x goes to 1 from the right, this factor that's being squared is approaching 3. And then this bottom factor is approaching 3. But of course the top is being squared. So all in all, we're going to get a factor of positive 3 times the limit as x approaches 1 from the right of 1 over x minus 1. And again, because x is greater than 1 and approaching 1 from the right, x minus 1 is going to be approaching 0, so it's going to become a small number, but it's going to be approaching 0 from the right as well. So it's going to be remaining positive. So think this is like starting at 1.1, 1.01, 1.001, etc. So this denominator is getting smaller and smaller and staying positive. So that means in the limit, this is going to infinity, and multiplying by 3 is not going to change infinity. 3 times a really large positive number is still a large positive number. So the limit is infinity. Now what about the limit as x approaches 1 from the left? Well, we're going to do the exact same thing. Okay, and so we're again going to get a factor of 3 for the same reason up here. I can use the limit laws to take the limit of this and this. I'm going to get 9, 3 squared over 3, times, the interesting part is the limit as x approaches 1 from the left of 1 over x minus 1. So what's going on here? Well, it's the same thing as up here. As x approaches 1 from the left, this is going to be a small negative number. So 1 over a small negative number is going to be a large negative number. And if I multiply by 3, again, that doesn't change the fact that I'm getting a large negative number. So as x approaches 1 from the right, I'm getting infinity. And as x approaches 1 from the left, I'm getting negative infinity. So this is enough to conclude that x equals 1 is a vertical asymptote for this function. So now let's consider the case a equals 2. Sorry, a equals negative 2. But notice that because we're going to be taking the limit as x approaches negative 2, we can assume that x is not equal to negative 2. In which case, look at what happens to f of x. We can actually cancel one of the factors of x plus 2. Again, because those factors are not going to be 0 since x is not equal to negative 2. So near negative 2 but not equal to negative 2, f of x is actually just x plus 2 over x minus 1. But look how nice this becomes. I can just take the limit as x approaches negative 2 of this function. I can do the right-hand limits and the left-hand limits simultaneously because it's going to exist. Because in fact, there's no problem here. This is not an indeterminate form. I'm not dividing by 0. This function is actually continuous in negative 2. It's a rational function. So this limit is actually just equal to f of negative 2, not f of negative 2. So this function here of negative 2, so it's equal to negative 2 plus 2 over negative 2 minus 1, but this is 0. So actually the limit as x approaches negative 2 of f of x is 0. But that means there's not a vertical asymptote at x equals negative 2. Okay, so here's an interesting limit. The limit is x goes to infinity of sine 2x divided by x. And so at first glance, well, first of all, note that this is not like a sine x over x limit because x is not going to 0. X is going to infinity. So how do we deal with this? Because sine is going to be oscillating from negative 1 and 1, and the denominator is going to be getting really big. So what do we do here? Well, intuitively, that's exactly what we can think. Sine 2x is just bouncing between negative 1 and 1. And since the denominator is going to be growing very large, we're basically just taking a small number and dividing it by a big number. So we might expect that this limit to be 0. Let's see why that is. So to show that, we're actually going to use the squeeze theorem. And we're going to use this inequality that sine theta lies between negative 1 and 1. This is a very useful inequality, and we'll use this over and over again. So now what I can do is I can assume, first of all, since I'm taking x to be infinity, that x is not 0. So I can actually divide through, well, first of all, let's replace theta with 2x. So I'm just letting theta be 2x here. This is still true. Now what I can do is I can actually divide everything by x. And recall that the limit as x goes to infinity of 1 over x is 0. But the same thing is true for the limit as x goes to infinity of minus 1 over x. It's just approaching 0 from the left instead of from the right, but it's still going to 0. So then we can conclude by the squeeze theorem that this middle limit, because this inequality is actually true for all x, we can conclude that this limit that we're looking for, because it's squeezed between two functions that are approaching 0, that this middle limit really is zero. And again, that's by the squeeze theorem. So anytime you have something that you suspect is going to 0, a lot of times it's nice to use the squeeze theorem to kind of bound it between two things that you know are going to 0. These trig functions are good examples because while they're not leveling off as x goes to infinity, they are remaining bounded as x goes to infinity. So if I'm making that bound smaller, 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 the limit really will be going to 0. And the squeeze theorem is a great way to really justify that. So here's another limit that we're taking as x goes to infinity. Now the red flag here is the square root. So you may ask immediately, what do we do about this square root? Now if the square root wasn't there, this would just be a rational function and we could do our same tricks. But what do we do with the square root? Well, this is where we actually use the fact that square root of x is continuous. So what does that really mean? Well, that means for a function, we can actually evaluate the function at a point to find the limit. So basically what this is saying is that we can say this limit is equal to the square root of the limit as x goes to infinity of this rational function we're taking the square root of. So we have a little side problem. Let's actually take the limit as x goes to infinity of 8x squared minus 3 over 2x squared plus x. So recall, what we need to do is factor out the highest power of x from the numerator and denominator. And they're actually both the same here. They're both x squared. So I factor out an x squared from the numerator, and I can factor out an x squared from the denominator. And these reciprocal powers of x are going to go to 0. I can cancel the factors of x squared because I'm assuming that x is going to be far away from 0, so x is not going to be 0. And so what I get is that this is just the limit as x goes to infinity of 8 over 2. And that's consistent with our rules about rational functions and their end behavior. So the limit really is 4. So going back to what we're looking for, this limit inside the square root here is 4. So the answer is just square root of 4, which is 2. So these facts about functions being continuous are really useful, because if you're taking the limit of a complicated function, the square root of something, or maybe something squared, or sine of something complicated, what you can do is you can actually take the limit of what's on the inside first, and then perform the operation. And so again, that's using the continuity. And here, we're just taking the limit of a rational function, pretty straightforward, and we get 2. Okay, so here's a seemingly simple limit, but you got to be a little careful. So the first thing that we can do is we can actually at least just factor out a 2, because the 2 is really not affecting the limit. Okay, I'm not saying that's a very enlightening step, but at least now we see that we're really just taking the limit as x approaches 0 from the left of 1 over x to the 2/5. Okay, Now remember, if this was just 1 over x, then the limit as x approaches 0 from the left, we would be taking 1 and dividing by a small negative number. So that would be going to negative infinity. But the interesting thing here is that this denominator, x to the 2/5, is always positive, right? Because I'm squaring something that's going to take a negative number and make it positive. And it's going to take a positive number, keep it positive. 0 is, of course, going to go to 0. And then taking the 5th root, but that's also still just going to be a positive number. So as x approaches 0, either from the left or right, it doesn't really matter, this denominator is staying positive. So I'm taking 1 and dividing by a small positive number. Even though I'm plugging in small negative values for x to the 2/5 is staying positive. So the limit here is going to infinity. And of course, multiplying by 2 is not going to do anything. That's just going to take a large positive number. Multiply it by positive 2 is still going to be a large positive number. So the limit is infinity. Now, of course, if this had been an odd power, if it had been x to the 3/5, it still would have been negative infinity because these numbers would have been remaining negative. It's all about the parity of the power, whether it's odd or even. So it's just something to look out for. So everything seems to get a little bit trickier when we deal with trig functions. But we want to attack this exactly the same way. First of all, tangent theta is kind of a compound function. What is it really? It's really sine divided by cosine. So let's start by replacing tangent with sine over cosine. So we have sine theta over cosine theta. Now let's use the limit laws. At least for the numerator, I can just evaluate sine at pi over 2. Because sine is continuous, theta is approaching pi over 2 from the right. This is really just going to go to 1. So this is equal to the limit, because this is going to 1, theta approaches pi over 2 from the right, of 1 over cosine theta. Now here's where you really have to use your trig knowledge. As theta approaches pi over 2, cosine is approaching 0. But it becomes significant whether cosine theta is approaching 0 from the right or from the left as pi over 2 approaches, or as theta approaches pi over 2 from the right. So let's actually just sketch cosine really quick. So recall, here's theta. Here will be pi over 2. Cosine is going to start up here and dive bomb through pi over 2 and then continue off that way. So we see as theta approaches pi over 2 from the right, cosine theta is remaining negative. So here, cosine theta, for theta just to the right of pi over 2, is negative. So we have 1 over a small negative number. This is going to negative infinity. So the principle is the same. 1 over a small positive number is going to infinity. 1 over a small negative number is going to negative infinity. It just becomes really significant that we think about what's going on with these functions we're dividing by. Now, if it's just x or x minus 1, it's pretty easy. But you see that when trig functions come in, you really do have to use your knowledge of the trig functions. So every time you think you're getting the hang of something, I always throw a curveball at you. But I think it's good to see a lot of different types of limits in the shapes and form they can come in, just so you can start getting a handle of what all you can see. So this looks ridiculous if you've never seen it before. Okay, so up until now, there's always been kind of a rational function aspect to the limits we're taking. There's a numerator and a denominator. What's going on? Well, let's just think about what this equals informally. So if I look at this first factor, square root of x plus 9, it looks like that's going to infinity, as x goes to infinity. And then I'm subtracting this factor of square root of x plus 4 that's also going to infinity, as x goes to infinity. So I'm getting infinity minus infinity. What is that? I mean, that doesn't even make sense. And it shouldn't make sense because this is another example of an indeterminate form. And just like 0 over 0, all I mean by indeterminate form is that this does not make sense. I'm not able to determine what this limit is in its current form. So what do we need to do? We need to do more work. And actually the nice thing here is we can use a red flag that's come up before. We see square roots. Now when we see square roots, what did we do when we were taking limits? Well, when we got indeterminate forms before, there was this trick called multiplying by the conjugate. That's exactly what we're going to do here. So this is equal to the limit, as x goes to infinity, of, well, square root of x plus 9 minus square root of x plus 4. So I'm going to multiply that by the conjugate. So remember the conjugate, there are two terms, one or both involving a square root, separated by a plus or minus. I'm going to multiply by square root of x plus 9 plus square root of x plus 4. But I can't do that for free. In order to do that, I also have to divide by the same factor. Okay, and notice that this factor is never 0, which is really convenient because we need it to never be 0. Okay, so why did I do that? Well, what's going to happen in the numerator? This is a difference of squares. So I'm going to get x plus 9 minus x plus 4 all over square root of x plus 9 plus square root of x plus 4. Okay, so let's keep going. What's going to happen here? The x's are going to cancel, and I have 9 minus 4. So I have 5. But the 5 really isn't going to make a difference. So we just have 5 times the limit as x goes to infinity of 1 over square root of x plus 9 plus square root of x plus 4. Now to take this limit, we can just think about it, and we can actually just see what the answer is by reasoning. So the numerator is 1, and the denominator is always going to be a positive number that's getting bigger and bigger and bigger as x goes to infinity. So we have 1 over a big number, which should be going to 0. And that's exactly the case. So in order to justify that, what we need to do is really factor out the largest factor of x from the denominator. And what we see is that this is equal to 5 times the limit as x goes to infinity of 1 over, I'm going to factor out an x squared. Now why did I factor out an x squared? Because really, if I have x inside, I'm sorry, not x squared. You're about to be really confused. No. I'm going to factor out, okay, what is the highest power of x? It's square root of x. Okay, but the way I have to do this is a little tricky. So I'm going to factor out a square root of x, and then what am I going to be left with? Well, in the first term, I'm going to be left with, okay, I factored out a square root of x, but I also factored out a square root of x from the 9. So this is going to be square root of 1 plus 9 over x. And again, if I just multiply the square root back in, the square roots combine using the properties of exponents, and I just have x plus 9. And then I also have 1 plus 4 over x from that term. And so what's the point? I mean, maybe this is kind of overkill. Maybe you just believe my reasoning. But the point is that this factor is going to 0. This factor is going to 0. So I have 1 over 1 plus 1, and then 1 over square root of x. So all in all, that's going to be 5 divided by 2. I mean, the 1/2 is not going to matter. Limit as x goes to infinity of 1 over square root of x. But this is 1 over x to a half, and we've talked about how 1 over x to a positive power is going to 0 as x goes to infinity. So there's kind of the overkill justification of y is 0 using just the facts we introduced in this lecture. But, I mean, the reality is, and the way I think about it, is you have a limit where you have a fixed number over something that's getting really large. Well, that's getting really small, so it's going to 0. So sometimes the intuition is really all you need to carry with you. The justification is just details. But that's kind of a strange example of an infinite limit, a different type of indeterminate form. It's an indeterminate form that we'll study later on, and we'll see even more types of indeterminate forms. But hopefully this gives you a sampling of the types of limits that you can see.